Flipped classroom video for Maths A2 Unit 3 Compound Angle Formulae. Compound angles, trigonometric functions and alpha plus beta degrees. Is there a connection between cos alpha plus beta, sine alpha, sine beta and cos beta? They're all geometrical functions, so there's a fair chance that there is. We've got this diagram set up, so we have the angle at O, we have an angle alpha plus beta there. We've also obviously got separate alpha and beta angles, and we've got a fair few right angles around the place, which means we can possibly chase some angles around as well. So let's get started. If we look at the triangle ODB, then we've got cos of alpha plus beta is the adjacent, so that's the O to D, over the hypotenuse, which is O to B. So we have established what cos of alpha plus beta is in terms of the geometry of this situation. We can see that OD is equal to OE take away DE. So, because DE and XA are the same, those two right angles, the right angle at D and the right angle at E, mean that the lines going up are parallel, and therefore the distance XA is the same as the distance DE. Then we can say that OD is equal to OE minus XA. Now the reason we're looking at what OD might be also equal to is that if we can get these other trig functions involved by using other triangles within this figure, then we can replace OD by these other things and we can make some sort of equation that connects them together. Now, using Z angles, we can see that XA is parallel to DE, parallel to ODE, because of the way the right angles are there, and that means that the angle at A, OAX, or XAO, must be the same as AOE, or alpha. That means we can write alpha in there. BAX is 90 take away XAB, and that means that angle in there is 90 minus alpha, and that means the angle at the top, ABX, must be 90 take away that, and 90 take away 90 minus alpha is indeed alpha again. So that's what I refer to when I say chasing angles round. So we've got alpha there now, and that means if we look at the triangle XAB, then we have that XA is the opposite of alpha, and BA is the hypotenuse within that triangle, so that must be sine alpha. And that means that XA is equal to BA sine alpha. Now, that means we've got XA in another form, so looking back up to equation 1, we're wanting to replace XA by something else, so that's good. We've got a sine alpha in there, which could be useful. Let's have a look at the triangle OAE, and within that triangle, that has alpha down as the angle at O, and so we've got the adjacent OE over the hypotenuse for that triangle, which is OA, and that is cos alpha. That means that OE is OA cos alpha. So now we have a replacement for OE in equation 1. In fact, we can say that cos alpha plus beta equals, well, we're replacing the OD from the first line of the whole job by our OE minus XA. So that gives us OE minus XA over OB. That's using equation 1. Then we split that off into two fractions, and now using equation 3 we can replace OE by OA cos alpha, and using equation 2 we can replace XA by BA sine alpha. Now if we look at the triangle now OAB, we can see that OA over OB is the cos of beta, because that's the adjacent over the hypotenuse for that one. And we can see that BA over OB is the sine of beta. And that means we can substitute those back into the line above, and we get cos of alpha plus beta equals cos alpha cos beta, take away sine alpha sine beta. And you could have a go at using this diagram to find out what sine alpha plus beta equals. You can do it in a similar way. It is in fact shown in one of the FMSPW exam question revision videos, and so if you wanted you could check that out there. Or it may be that your teacher does it with you anyway. So that is one of the compound angle formulae. It's the compound angle alpha plus beta, and we're finding the cos of it. So that's the one we've seen. Cos of alpha plus beta is cos alpha cos beta, take away sine alpha sine beta. From this we can derive that cos alpha minus beta is cos alpha cos minus beta, take away sine alpha sine of minus beta. And cos is an even function, which means that cos of minus beta is equal to cos of beta. Sine is an odd function, sine of minus beta is equal to minus sine of beta. And by subbing those back in, we get cos of alpha minus beta equals cos of alpha cos of beta, take away minus sine of alpha sine of beta, and we end up with cos of alpha take away beta is cos alpha cos beta plus sine alpha sine beta. For sine, we can do this geometrically, but it turns out that sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. And similarly, if we replace the beta by minus beta and jiggle it about, we get that sine of alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. Now for tan, we can do that geometrically, of course, or we could use our previous results. So tan of alpha plus beta is equal to sine of alpha plus beta over cos of alpha plus beta. Subbing in from the previous results we've got, that means we have sine alpha cos beta plus cos alpha sine beta over cos alpha cos beta, take away sine alpha sine beta. And now, and it's starting to look a bit messy, but we divide all terms by cos alpha cos beta. So that's basically dividing the top of this fraction and the bottom of the fraction by cos alpha cos beta. So first of all, we can cancel a number of things. Top left, we can cancel cos beta from the top and bottom of the fraction. Top right, we've got cos alpha over cos alpha, which cancels. Bottom left, we have cos alpha over cos alpha and cos beta over cos beta, so that all cancels out to leave us with 1. And then bottom right, there isn't any cancelling. What we can now do, though, which is rather nice, is that we can replace all of these sines and coses by tans. So we've got sine alpha over cos alpha top left gives us tan alpha. We have sine beta over cos beta top right, which gives us tan beta. And on the bottom of the fraction, we have 1 minus. We've got sine alpha over cos alpha times sine beta over cos beta, which is the same as tan alpha times tan beta. And just for completeness, if we do again a similar job to the previous one, replacing beta by minus beta, we end up with tan of alpha minus beta is equal to tan alpha minus tan beta over 1 plus tan alpha tan beta. And that's because tan is an odd function, so that's how that works. We can use these identities, in fact they are, for solving certain problems or finding things out, and one of the things we can do is find out the exact values of some angles. So sine 75, that will be the same as sine of 30 plus 45. Now to proceed, we need to know all these standard results, which you probably do know by now. If not, get on with learning them because you need to know them. We can now split sine 30 plus 45 into sine 30 cos 45 plus cos 30 sine 45, and then we can take the fractions from our green and yellow table in the middle there, and that means we have a half times root 2 over 2 for the first part of this, and root 3 over 2 times root 2 over 2 for the second part. And if we tidy that up, we get root 2 plus root 6 all over 4. Cos 105. You've always wanted to know. Cos 105 is the same as cos 60 plus 45. That's going to be cos of 60 cos of 45. Take away sine of 60 sine of 45, which is a half times root 2 over 2. Take away root 3 over 2 times root 2 over 2, which gives us root 2 take away root 6 over 4. Tan of 15. Well, you can probably guess what's going to happen for this one. Yes, you're right, it's tan of 45 take away 30. That's going to be tan 45 take away tan 30 over 1 plus tan 45 tan 30. We pop the fractions in. 1 take away root 3 over 3 divided by 1 plus 1 times root 3 over 3. If we times the top and bottom of these fractions by root 3, we end up with 1 times root 3 is root 3. Root 3 over 3 times root 3 is 3 over 3, which is 1. So we get root 3 minus 1 on the top. On the bottom we have 1, which when we times by the root 3 is root 3. Then we have 1 times root 3 over 3, which is root 3 over 3. We need to times that by root 3, which gives us 3 over 3, which is 1. So, finally, tan 15 is root 3 minus 1 over root 3 plus 1. We could, of course, do that in a different way using our standard results. We could say, oh, we'll call it tan of 60 minus 45. That means tan of 60 minus tan of 45 over 1 plus tan 60 tan 45. That is root 3 minus 1 over 1 plus root 3 times 1, which gives us the same answer, of course, of root 3 minus 1 over root 3 plus 1. We can also express tan 15 as 2 minus root 3, but I'll leave that as an exercise for you to do, dealing with the surd situation there. Now, the fact that all these can be done like this points to the other fact that all of these things can be derived geometrically by doing geometrical splitting of angles and so on. And it's all very beautiful when you do it that way. It's pretty good this way as well. Rather nicer than a calculator, apart from if you need these values simply to finish some sort of calculation, in which case calculators are great.